Hey, welcome to the channel. If this is your first time here, shout out to you for making it out. If you've already seen one of my videos before, you're most likely one of my students, so you're lucky to have me to make these videos for you guys. If I don't have you as a student, I appreciate you actually coming back to watch more and more of my videos. All of the views, the interactions, it really makes a difference, so I appreciate that. Today's video is going to be about mole conversions. So we're going to use our diagram here to kind of be our guide through each of the different problems that we're going to see today in the video. So to start off, we're going to break down what does this diagram actually mean for us. So everything that's circled, these are units that we're going to be able to perform conversions to either cancel out or to attain through some type of converting factor. So we have moles in the middle. Moles is going to be the middle ground for all of the units that we're going to see today. Without moles, we really wouldn't be able to go between liters, grams, and particles. So we'll see moles and moles a lot throughout this entire video. So we'll start off at the top of the diagram. So we have liters. When we think about liters, it's a unit for volume. And so a converting factor for liters between liters and moles is going to be molar volume. Molar volume is this value of 22.4 liters per 1 mole at STP. STP stands for standard temperature and pressure. So standard temperature is 0 degrees Celsius, but if we have it in units of Kelvin, it'll be 273 Kelvin. And P stands for pressure, and standard pressure is going to be 1 atmosphere. So if we do not have these conditions, standard temperature and standard pressure, we are not going to be able to have this equivalence of 22.4 liters for every 1 mole of a substance. When we think about grams, grams is going to be a little bit different. Our converting factor between moles and grams is going to be molar mass. Now, something really important to talk about is that molar mass is not the same for every substance. The way that we're going to find molar mass today is by using the periodic table. Each individual element has its own atomic mass. And so if we're looking at, let's say, methane of CH4, comparing that to ethane of C2H6, they have different amounts of each element. And so they're not going to have the same molar mass values. So when we talk about molar mass, it is specific to the substance that is being measured. And so we'll come back to this. When we look at the converting factor of molar mass, it is some number of grams for every 1 mole. So like I was saying, molar mass is specific to each substance. So that numerator part of our converting factor is going to vary depending on what substance we're looking at, but it'll always be some amount of grams for every 1 mole of that substance. Our third converting factor is going to be Avogadro's number. Avogadro's number is going to help us convert between the units of moles and particles. When we think about the converting factor of Avogadro's number, it is 6.022 times 10 to the 23rd power number of particles for every 1 mole. So if we have 1 mole of a substance, we will have exactly that many particles of that same substance. So those are the 3 converting factors that we're going to look at today. Like I said before, everything's going to have to go through moles in order to get somewhere else. So let's start working through some practice problems and get some examples going to see how can we actually use each of these different converting factors. Our first example is asking how many grams are in 2.5 moles of H2O. Whenever we're looking at a problem that requires a conversion, we have to think about 2 things. What are the units that we're starting with? And then what units are we trying to convert to find? So I'm going to use given and wanted very frequently throughout this video. So the given is going to represent what we already know, what we already have. And so for this specific example, we know that there are 2.5 moles of H2O. So this would be considered the given. The wanted is what we're looking to find. What are we trying to convert moles to become? It then asks in the beginning, how many grams are there in 2.5 moles of H2O? So the grams are going to be the wanted value, the units we convert to have. So we're going to use this technique called dimensional analysis, where we are setting up a series of fractions in order to cancel out our units to obtain the final units. So the given value is always going to get its own fraction, right? That's always going to be consistent. So our first fraction is going to contain the given, which is 2.5 moles over 1. We're just going to throw it over 1 to force it to become a fraction. Each converting factor we use is going to be another fraction. So in order to go from moles to grams, we have to think about what converting factor are we going to need. If we think back to the diagram in the beginning, in order to convert from moles to grams, we are going to need the molar mass of the substance. The substance that we're using here is H2O, so that means we'll have to use the periodic table to find the atomic mass of 2 hydrogens and then the atomic mass of 1 oxygen. If we get the sum of those, that is going to be our molar mass of H2O. So if we have one fraction for the given and then one fraction for our converting factor, that should tell us how many total fractions we're going to need for our dimensional analysis. So that means we'll need 2 fractions in total. So let's set up our chart here, and this is what we're going to start with. So we're going to put our given units, our given value, into its own fraction, the first fraction. So we have our given in our first fraction. Like I was saying before, we can just throw it over 1 to force it to become a fraction. You can leave the denominator blank. That part is up to you, but you're never going to have units in the denominator unless the provided units are already in a fraction format, but they're not, so that's just going to be our numerator value. Now, like I was saying, we need the molar mass that is specific to H2O in order to find grams of H2O. So using our handy-dandy periodic table, we know the molar mass of water is going to add up to be 18.015 grams per mole. So for every 1 mole, we have 18.015 grams of water. So we have to think, how can we put that into a fraction? So the purpose of dimensional analysis is to get the units to cancel out so that we are only left with the units that we want. So moles are in the numerator of our first fraction, so that means that moles will have to be in the denominator of the second fraction so that we have them cancel. Anything divided by itself is equal to 1, so we will no longer have those units. So we have moles in the denominator, right? We have to think, what's the other part of our fraction? So if moles is 1/2 of the units for molar mass, grams is going to be the other half. So if moles are in the denominator, that means grams will have to be placed into the numerator. You're never going to put grams per mole in one part of your fraction for dimensional analysis. That's just not how it's going to be. You should only have 1 unit for each part of your fraction. So now we have to think, where do the numbers go? So it's 18.015 grams per mole. So it's per 1 mole. So mole is always going to get a value of 1, no matter where it is. And then the actual molar mass value goes with the units of grams. And so that is going to be 18.015 grams. If we look at this, this is representing water, H2O. And we have to then think about, okay, well, what units cancel? Moles of H2O are diagonal from each other, so they cancel out, so we don't see those units anymore. Grams of H2O are the only ones that are left, so we know that our final value will be in the units of grams, and that's exactly what the question is asking for. So we know that we at least set the units up correctly. You then have to think, okay, well, are we going to multiply or divide by this converting factor? If the number is in the numerator for your converting factor, that means you are going to multiply by that converting factor. So we have 2.5 times 18.015. So this is going to give us grams of H2O. Our initial value, our given, has 2 sig figs, so that means our final answer is also going to need 2 sig figs. So when we do the calculation, we get 45.0375, but because we only need 2 sig figs, we only keep the first 2 significant figures in this answer. So we are going to get an answer of 45 grams of H2O. Let's look at another example. This time we are going to find out how many particles are in 2.5 moles of H2O. So it's the same first step. We want to identify what is the given value and what is the wanted. The given value is going to be 2.5 moles of H2O, and then the wanted value is going to be the number of particles. So given value gets one fraction, and our converting factor is also going to get another fraction. We only need one converting factor to go directly from moles to particles. And if we think about the diagram, that is going to be Avogadro's number. So we're going to set up two fractions. Our given value is still going to be the numerator of our first fraction. Now we have to think about our converting factor. Our converting factor here is Avogadro's number. So it's 6.022 times 10 to the 23rd number of particles for every 1 mole. So we want to cancel out units of moles here. So moles need to be diagonal from each other. So we have moles of H2O in the denominator for our second fraction. And then this is going to be moles to particles. And so particles is going to be in the numerator. Now we have to think about where do the actual numbers go. So like I was saying, for every 1 mole of H2O, we'll have 6.022 times 10 to the 23rd power number of particles. Moles of H2O cancel because they're diagonal. Particles of H2O are the only units that are left. So our units are making sense here based on how we set them up. Avogadro's number is going to be in the numerator here. So that means we are going to multiply by the converting factor. So we have 2.5 times 10, we have 2.5 times 6.022 times 10 to the 23rd. We have still just 2 sig figs for our given value here. So that means our final answer should also be 2 sig figs. So when we do the math, we get 1.5 times 10 to the 24th power. And then that represents the number of particles of water in 2.5 moles. With this example, we're going to find out how many liters are in 2.5 moles of H2O at STP. So thinking back to our diagram, liters and moles, we're going to need molar volume. The only time we're able to use molar volume is if we have the standard temperature and pressure. So the scenario tells us that we are at STP, so we are assuming these standard conditions. So we are able to use molar volume to perform this conversion. We have the given value, 2.5 moles of H2O, and our wanted value is going to be the liters of H2O. One fraction for the given value, one fraction for our converting factor of molar volume, so that means we need 2 fractions for our dimensional analysis. Given value goes in the numerator of our first fraction. Now we have to think about how do we set up the converting factor in its fraction. So it's 22.4 liters for every 1 mole. We want moles of H2O to cancel, so they have to be diagonal. And then if we think about how the fraction of molar volume is set up, it's liters per mole. So if moles are in the denominator, that means liters will have to be in the other part of our fraction, which would be the numerator. So for every 1 mole of water, we would expect there to be 22.4 liters of water. Moles of H2O cancel because they're diagonal, leaving us just with liters of H2O, which is what we want. Now we just have to think, is this multiplication or division? The value for our converting factor is in the numerator, so that's going to be multiplication. We have 2 sig figs for our given value, so our final answer should also be 2 sig figs. So we have 2.5 times 22.4, which gives us 56. So we have 56 liters of water for 2.5 moles of water. Now, notice that there was a pattern for all 3 of these examples. We're starting with the units of moles, and we're looking for some other units. The first example was grams. then we thought about particles, and then lastly, we thought about liters. We multiplied for each of these conversions. If you are starting with moles and you are going outside to one of the three other units in the diagram, you are going to multiply by your converting factor. That is going to be consistent. Because if we think about how the unit's set up, moles always need to cancel. So if you're starting with moles, that means moles need to be in the denominator. If moles are in the denominator, that means that your converting factor will be in the numerator of that fraction. And so if we always have the converting factor in the numerator, that means you're always going to multiply by it. So that's why we're able to see this pattern consistently for starting with moles and looking for some other units. So let's see what happens if we're not starting with moles. For this example, we're looking to find moles when we have 8.30 times 10 to the 24 particles of CH4. So CH4 is going to be our given value with 8.30 times 10 to the 24th particles, so units of particles. And we're looking to find now the units of moles. So we're starting on the outside of our diagram, trying to work our way into the center where we have units of moles. Our converting factor between particles and moles is still going to be Avogadro's number. But what's different now compared to the previous example with particles is that we are starting with units of particles. So we have our given value, and we know Avogadro's number is going to be our converting factor. So that means we need two fractions. The given value is going to go in the numerator of our first fraction. And we can set that over 1 still. We don't have to, but you can if you want. And then we have to set up Avogadro's number in the second fraction so that we can convert from particles to moles. Now notice here, if we're starting with particles, we need particles to cancel out. So that means particles need to be diagonal. And if we think about Avogadro's number, if we're looking at particles, that means the other half of our fraction is going to be moles. So if particles are in the denominator, this time moles will be in the numerator. And it's still, for every 1 mole of CH4, we will have 6.022 times 10 to the 23rd power number of particles for CH4. Now, we still want the units to cancel. Particles of CH4 are diagonal, so we are able to get rid of those. We are left now only with units of moles, which is what we wanted to solve for. Now we have to think, is this multiplication or division? Our converting factor value, the number, is in the denominator here. So that means we are going to divide by this converting factor. So we will have 8.30 times 10 to the 24 divided by 6.022 times 10 to the 23rd. Our given value here has 3 sig figs, which means our final answer is also going to need 3 sig figs. So when we do the division here, we end up with 13.8 moles of CH4. We have another example here looking at 20.84 grams of CH4, but we want to convert to the units of moles. So the 20.84 grams of CH4 is going to be our given value, and then moles is going to be our wanted. That's what we're going to look to find, which means we are going to need 1 fraction for our given value, and we're going to need another fraction for the converting factor between grams and moles. Molar mass is going to be our converting factor if we're going between grams and moles. So that means we need the molar mass of CH4. So let's put our given value in our numerator first. And then let's find out what our molar mass is going to be. So using our periodic table, we look at the atomic mass of carbon and then the atomic mass of 4 hydrogens. We add all of those together, and then that is going to be our molar mass. So our molar mass here is going to be 16.043 grams per mole. We want grams of CH4 to cancel, so they need to be diagonal from each other. And then thinking about our units of molar mass, if grams is in one part of our fraction, that means moles need to be in the other part. So that means moles is going to go into the numerator. So for every 1 mole, we will have 16.043 grams. The molar mass is always going to go with the units of grams. No matter where you have grams in the fraction for molar mass, that is where you have to put the actual molar mass value. 1 is always going to go with the units of moles for your molar mass. Grams of CH4 will cancel. We'll be left only with moles of CH4. So it's looking good for us. Now we have to think multiplication or division. The molar mass values in the denominator, so that means we are going to divide with it. So we will plug in 20.84 divided by 16.043, and then that is going to give us the units of moles for our answer. Our given value is 4 sig figs, so that means we need 4 sig figs for our answer. So we are going to end up with 1.299 moles of CH4. Let's take a look at our last one-step conversion here. So our given value is going to be 0.615 liters of CH4 at STP, and we're looking to find the units of moles. So we have standard conditions for temperature and pressure, which allows us to use molar volume, so we're able to go from liters to moles using molar volume. One fraction for our given value and one fraction for our converting factor, which is going to be molar volume since we're dealing with units of liters. So we will use 2 fractions in total. The given value is going to be the numerator of our first fraction. And then we have our converting factor of molar volume. Molar volume is 22.4 liters for every 1 mole. So one part of our fraction is going to be liters, the other part of our fraction is going to be moles. We want liters of CH4 to cancel, so that means we need liters to be diagonal. Like I just said, if liters is one part of our fraction, moles will be the other part. That means moles is going to be the numerator of this fraction. So for every 1 mole, we have 22.4 liters. Liters of CH4 cancel, leaving us just with the units of moles. For CH4, molar volume is in our denominator here, so that means we will be dividing by it. So we will have 0.614 divided by 22.4. Our given value has 3 sig figs, so our final answer will also need 3 sig figs. So when we write out our answer, it's going to be 0.0275. If you want to put it in scientific notation, it can be 2.75 times 10 to the negative 2. Both of these are going to be the same value. So either one of these is appropriate as long as you are maintaining moles of CH4 as your units. For these last 2 problems, let's kick up the heat a little bit. So I said that the last example was the final one-step conversion problem. We are now going to look at 2-step conversions. 2-step conversions means that you're not necessarily going to start or end with the units of moles. Typically, you're going to start at one of the 3 outer points on the diagram and make your way to another outer point on the diagram. So for this example, we are looking at 1.01, we're looking at 101.09 liters of O2 at STP, and we want to find the number of grams. So at no point in this example does it say moles, but it is assumed that if we are performing some type of conversion here, we are going to need moles at some point in order to get to the other units. So we don't have the density of O2 provided to us, which means we can't just use density to go directly from volume to mass. At STP tells us that we are able to use molar volume to convert liters to moles, and then our next step would be moles to grams. So that's why these are called 2-step conversions. We are going to need 2 converting factors. to find the desired units at the end of this. So we have one fraction for our given value, and we need one fraction for every converting factor, which means since we're using two converting factors here, we're going to need three fractions in total. Our given value is 101.09 liters of O2. We're at STP, so we need liters of O2 to cancel out. So that's why I was saying we're going to use molar volume first. So our second fraction here is going to contain molar volume because that is the only way we can get liters of O2 to cancel, which will then give us moles of O2. So for every 1 mole of O2, we will have 22.4 liters of O2. Now notice, I'm not ending this off and then just writing out my answer in units of moles and then performing another conversion afterwards to then get to grams. I am able to show less work by setting all of this up with one-dimensional analysis setup. So we now need to go from moles of O2 to grams of O2. So our next converting factor is going to be the molar mass of O2. We want moles to cancel out. That's still consistent. So moles of O2 need to be diagonal. But if we're using molar mass now, grams is going to be the numerator of this last fraction. This is going to allow us to end with only grams. So if we think about the molar mass of O2 from the periodic table, it's the atomic mass of oxygen twice. So then we are able to get 31.998 grams per mole. So for every 1 mole of O2, we will have 31.998 grams. Now let's cancel out these units. Liters of O2, gone. Diagonal, we can get rid of them. Moles of O2, gone. Also diagonal, so that means that they're no longer there. We are ending just with grams of O2, which is exactly what we wanted. It asked us to calculate the amount of grams. So we are doing this effectively by setting up all of the units appropriately for them to cancel. So we have grams of O2. Now we just have to think about how do we solve for this. So molar volume is in the denominator of that second fraction, which means we will divide by molar volume. Molar mass is in the numerator of the third fraction, so we will multiply by molar mass. So when we plug this into a calculator, we have 101.09 divided by 22.4 multiplied by 31.998. Our given value has 5 sig figs, so our final answer should have 5 sig figs. So we will end up with 144.41 grams of O2. That is going to be our final answer. So this is a two-step conversion because we used two converting factors. Let's do this last example together, and then I think that'll be a wrap. Our given value here is 3.094 times 10 to the 21st number of particles of C2H4 at STP. We are now looking for the number of liters. As soon as we see units of particles, that should then tell you we have to use Avogadro's number. Whenever you see units of liters at STP, that should tell you you have to use molar volume. So we have two converting factors we are going to need for this. So that means this is going to be a two-step conversion. Two-step conversions require 3 fractions. 1 fraction for the given value, 1 fraction for each converting factor. At this point, placing the given value should be the easiest part. At least I hope so. Fingers crossed. So we're starting with particles of our C2H4. We want particles to cancel, so we need Avogadro's number. Particles need to be diagonal, and Avogadro's number tells us that if we have particles, we're able to have moles as well. So for every 1 mole, we are going to have 6.022 times 10 to the 23rd particles. Sorry, I wasn't consistent with my color here, but I apologize. So our next converting factor needs to get us from moles to liters. We're at STP, so that means we are allowed to use molar volume. So moles of C2H4 are going to cancel out, and if we're thinking about molar volume, that means we will end up with liters of C2H4. So for every 1 mole of C2H4, we will have 22.4 liters of C2H4. Let me just change these colors really quickly so that we're consistent. It's kind of bugging me. There we go, much better. Let's get cancel crazy. Particles, C2H4, gone. Moles of C2H4, gone. Leaving us with only liters of C2H4. So we did a good job. We set everything up appropriately, so we're able to make it make sense. Avogadro's number is in the denominator, which means we will divide by it. Molar volume is in the numerator, which means we will multiply by it. So we get 3.094 times 10 to the 21st divided by 6.022 times 10 to the 23rd multiplied by 22.4. That is going to give us liters at the very end of this. We have 4 sig figs for our given value, so that means our final answer should also have 4 sig figs. When we perform our calculation, we get 0.1151 liters of C2H4. Thinking about the diagram, you're always going to have to go to units of moles at some point. Moles is what connects liters to grams, grams to volume, connects particles to grams. Everything is interconnected with our diagram. So as long as you're relying on dimensional analysis to have your units cancel and you're using the correct converting factors, I don't see how you're able to go wrong with this. It definitely takes time, it definitely takes practice, but repetition is going to be your best friend when it comes to mastering dimensional analysis for each of these converting factors. If you now want to apply your skills of mole conversions to stoichiometry, you can check out my next video. I have that linked here on the screen. So thank you very much for watching this video. I really, really hope it helped. If you have any other requests for other videos, don't hesitate to comment here. I also post content on my TikTok page, chem_Hawkins. It's the same as my YouTube handle. All support is appreciated, and I really just hope that you're able to benefit from this.